Oops. Is my screen visible to everyone?
Yes.
Excellent. Good. So
Yeah, I see.
thank you for the invitation to give a talk here. So I'm going to tell you about some of my work which has something to do with algorithms. So I'm not at all a computer science person. I'm coming from random matrix theory and quantum information theory. But recently we were facing this this question which is related to algorithms, so to a kind of a synchron-like alternating minimization problem. So I thought this was a good topic for this type of for this meeting. So this is joint work with Simon and Moritz, who are now both in Germany. So this is the plan of the talk. So I'm going to tell you about the graph isomorphism game, which is kind of a recent and new take on the graph isomorphism problem. And what's interesting about this new approach to the problem is that, of course, it doesn't. I think it doesn't tell you much about the classical setting, but it allows you to generalize this graph isomorphism to kind of new settings, and kind of it's insightful for people working in quantum theory, and it allows you to do the same thing for other problems than graph isomorphism. So I think it's an interesting thing to review. Then I'm going to tell you about quantum permutation matrices and some kind of new type of symmetry for graphs coming from these quantum permutation symmetries. And then finally, I'm going to end on a slide about this algorithm we have to generate these quantum permutation matrices, which are generalization of the classical permutation matrices. And this kind of, maybe I can tell you about some open questions we have. I mean, the first one being just proving that the algorithm converges. So we don't even know that. But I will comment on this later. Good. Okay. So let me review briefly graph isomorphism. So the question here is that we have two graphs, G and H, and they are isomorphic if there is a map, a bijective map from the vertices of G to the vertices of H, such that it preserves adjacency and non-adjacency. And if you want to formalize this using linear algebra, the way to do this is that the two graphs G and H are isomorphic if there is a permutation matrix P which intertwines the two adjacency matrices. And this just means this relation here just means that the map F above maps the vertices of G to the vertices of H, and the map is given by the permutation which is encoded by P. So remember that the permutation matrix is just a 0-1 matrix, the property that on every column there is just one element equal to 1, the other ones are 0, and the position, the row in which you can find the element 1 on column J is sigma of J. And so this is a standard representation of the permutation. Okay, so basically we can the point here is that we can encode this graph isomorphism by this intertwined relation. Okay, so here is one of maybe the only slide that I want you to recall from this talk. It's this reformulation of the graph isomorphism question as a game. So here's the setting. We have two players, Alice and Bob. Here they are represented by A and B. And they play a game, so they play together. It's a cooperative game. They play a game against the referee R. And the goal is that basically everyone we have these graphs G and H, and the players A and B, they try to convince the referee that the two graphs are isomorphic, even though they might not be isomorphic. So they might want to cheat and try to convince the referee of some fact which is wrong, but that's the goal of the game. So the game goes as follows. So the two graphs are known to the three parties, and Alice and Bob can conspire before the game starts. They can discuss, they can establish a strategy, and then the game starts. And once the game starts, they are no longer allowed to communicate. And here is how the game goes. So the referee R, he's going to ask questions. So he's going to ask questions G and G prime to Alice and Bob. So he's going to send G So let's say here G and G prime can be vertices of G, let's say. So he's going to send a vertex of G to a vertex and a different vertex or the same to Bob. And Alice and Bob are going to reply with vertices of H. Okay? So they're going to reply with vertices of the other other graph. And then the referee will look at the answers, and he will decide whether Alice and Bob won the round. And the referee says win if the relation between G and G prime is the same as the relation between H and H prime. And here, what is this this relation? Let's look at it for two vertices of G. So it can take three values. It can be so the relation is defined to be equal if G equals G prime, adjacent if G is adjacent to G prime in H, and non-adjacent if G is non-adjacent to G prime in G. Okay. So if Alice and Bob get asked the same vertex, they have to reply with the same if they are asked identical vertices in G, they have to reply with identical vertices in H. If they're asked adjacent vertices in G, they have to reply with adjacent vertices in H. And if they're asked non-adjacent vertices in G, they have to reply with non-adjacent vertices in H. And here is the first result. The first result is that G is isomorphic to H if and only if the players Alice and Bob, using just classical resources, so they are not allowed to use quantum mechanics, they can always win this game. And this is not hard to see, because if the graphs were indeed isomorphic, and if Alice and Bob knew an isomorphism between G and H, then Alice and Bob will simply reply with f of G and f of H prime respectively when you are asked G and G prime. So you see this when they reply with f of G and f of G prime, this relation condition is satisfied. And basically what this theorem says is that they cannot cheat. So if the graphs are not isomorphic, there is no such isomorphism, so there is no winning strategy. So this is kind of the result for the classical. Now we're going to switch gears and go into the quantum world. And we have the following definition. We say that G is quantum isomorphically to H. If now quantum players, I will tell you in one instant what quantum players mean, can win this. Okay? So now this quantum isomorphism will be a relaxation of the classical isomorphism, because these quantum players now they have access to quantum mechanics. So they have more resources. They have more resources in their goal to cheat to cheat and win the game against the referee. So this quantum isomorphism will be a relaxation of the classical isomorphism, because, and indeed we'll see that there are graphs which are quantum isomorphic but not classical. So there are graphs which are not classical isomorphic, but they are quantum isomorphic. So what is this quantum? So what is quantum player? So quantum players means that the players are going to answer in a random way. So they are the game is the same. The referee will ask questions G and G prime. The players will have to answer H and H prime. And the way this goes is that the player will answer randomly, and they will give answers H and H prime given the questions G and G prime, using a formula which using quantum mechanics. So what does this mean? Let me first write down what the formula is, and then I will explain what this is. So there is this quantum state psi. I'll tell you in a moment what this quantum state is. And then Alice will use something which is H given G, H prime given G. So what are the objects here? So psi is a quantum state. So psi will be a unit vector in some Hilbert space, in some tensor product Hilbert space. So this is a quantum state. And what are these E and F? So E, So this object, let's say H in vertices of H, this is a quantum measurement. So this means that these are operators. These are positive semi-definite operators, which sum up to 1. And so these are like for Alice, and these are the operators for Bob. So what Alice and Bob will do, they are going to share this. They have this shared quantum state psi, which they can share it before the game starts. This is a resource. So before the game starts, they are in the same room. They discuss, and they take like 2 entangled particles, and each one takes its particles, and they go into separate rooms. They are no longer allowed to communicate. And once they get questions, once Alice receives the question G, she looks in her room, in her lab, and she chooses a measurement apparatus which depends on the question she had, the question G. This is this E of H given G. And then she performs this quantum measurement on her particle, which is like entangled with Bob's particle. And then the measurement apparatus will show the answer H, will show outcome H. And this is what she answers the referee. Okay? So this is what the axioms of quantum mechanics tell you that you are allowed to do. And this respects the rules of the game. So they first share this quantum state psi before the game starts, and then they are no longer able to communicate. So you see the Alice's choice of measurement doesn't depend on Bob's question G prime. So there's no communication during the game. And they can answer. So the effective answers they provide to the referee are given by this conditional probability P of HH prime given GG prime. And these are called quantum strategies. And if they can always win this game, so whenever they will always answer in such a way that this relation of G and G prime equals the relation between H and H prime. If they can always win the game using these quantum strategies, we say that the graphs G and H are quantum isomorphic. So there is a subtlety here. Here I'm using this tensor product. So what I'm using here is what is called the spatial quantum, the spatial strategies. There is another formulation where here, instead of using this tensor product operators E and F, I'm using a single Hilbert space, so there's no tensor product, and I'm asking that these operators should commute. And this is called the commuting framework. This is just like it's a subtlety. It's a technical subtlety. It's important. I'm not saying it's not important, but maybe it's too much for the time I have for the stock. So I'm going to just to not discuss. And here is, excuse me, is there a question or no? Okay. I cannot see the chat. So if there is a question, please just say it out loud.
I do have a question. So does Alice know G prime and Bob knows G?
Of course not. Alice only knows G. So okay. that's the whole point, because if Alice and Bob, if both knew G and G prime, they could always win trivially at this game. I mean, they could decide, if you get asked G and I get asked G prime, then we just answer H and H prime, and we do this. We just need, okay. We can just write down the strategy before the game starts. The whole point is that they are separate. They are spatially separated. So once the game starts, Alice only gets her question G. She has no idea about Bob's question, right? I mean, that's the main difficulty. I mean, this is why all of this makes sense. I mean, so Alice only knows G, and she has to answer H only depending on G. And in this quantum case,
because
she can use this
G...
resource. Yes, please go ahead.
Yeah, I'm a little bit puzzled because if G is equal to G prime, they have to answer with H equal H prime. But...
Yes, but they can just at the beginning of before the game starts, they can say, well, look, if we ask if we get asked vertex 1 of the graph G, we always answer vertex 5 of the graph H. This they can do. They can write on a piece of paper, and once the game starts, they can look at this piece of paper and do it. But of course, this doesn't mean that they can win the game. But they can satisfy this condition. This is not a problem. If they were always if they were asked the same question always, I mean, this has nothing to do with the graph structure. So it has nothing to do with graph isomorphism. But it's a constraint that we definitely want to ask. We want to impose. But this they can decide. They can strategize before, and remember that they know what the graphs G and H are.
Yeah. And then one more question about.
Sure.
So this theorem that you have at the bottom. So what if instead of sharing an entangled state, they share just random bits? So they're still classical, but they share random bits. Is it still true that?
Yes, this falls into the first theorem that even if they are allowed to have shared randomness, then the theorem still holds. So in classical pairs, I can allow shared randomness because by an extremal point argument, you can show that this among the random strategies, the best one will be a deterministic one. So actually, the shared randomness doesn't hold. Because remember, we are asking probability 1. They should always win the game, right? But that's a very good point. So shared randomness is allowed in the classical setting. And basically in this quantum setting, we are replacing this shared randomness, shared resource by a quantum resource, which is this entangled state itself. And again, if the state psi is not entangled, if it's kind of a classical quantum state, if you like, then this amounts to shared randomness. So we are back in the classical setting. So we need like a pure quantum resource here. Very good. Thanks for the question.
Thank you.
All right. So this was the definition, right? The definition is two graphs are quantum isomorphic if this relaxation of the graph isomorphism gave to quantum pairs allows the player to win the game. And now we have a mathematical theorem. So by the way, I haven't given any references, so I will not actually. But if you want to know more about this quantum isomorphism, the names you have to Google is Laura Manchinska and David Robertson, which are now in Copenhagen, and they have done most of the work about this. So these are the names that you have to remember. So basically, we have a characterization of quantum isomorphism for graphs. So two graphs. Let's first look at the theorem. Two graphs are quantum isomorphic if and only if we have the same relation as in the classical setting, but now P is, instead of a classical permutation matrix, like usual permutation matrix, we have a quantum permutation matrix. So this is very similar to the classical case. We just add the word quantum. Let me tell you now what is a quantum permutation matrix. So remember, a classical permutation matrix was just 0s and 1, and on every row and every column, you just had exactly one entry equal to 1. And this is kind of the same, but you have to replace scalars with operators. So here is the definition. So now the entries of the matrix are no longer numbers, but they are elements of a C-star algebra. So think about like infinite dimensional matrices. And the two requirements are just translation of the fact of the two properties that I've given you for classical permutation matrix. So the entries have to be, in the classical case, they had to be 0 and 1. Now replace this by the fact that they have to be projections. So they should be idempotents and so adjoint. So real numbers, and they should be equal to their square. So Pij is a projection. And we have this, there is only one in every row and column. And this is saying that the sum of these entries should be equal to 1. So if you have, 0s and 1s, this is the same that the sum is equal to 1, and the same here. So this is what a quantum permutation. So you basically have a matrix of projections, and the sum of rows and columns have to be the identity element, so the identity projection, the projection of the whole space. Okay, these are quantum permutation matrices. And there are, of course, so recently Manchinska and Robertson gave a different, more combinatorial characterization of quantum isomorphism, but I won't go into this. And since my time is getting shorter, I still maybe have 2 minutes. Let me tell you about the algorithm, right? I mean, so what we did in this paper with Simon and Moritz was that we wanted to generate these kind of objects. So these matrices of projections, which such that the sums of each row and column are equal to identity. So we came up with the following algorithm. So you see here the conditions that the first condition is that the elements needs to be projections. So here we looked at the simplest case where these projections are rank 1 projections, and where our actually so what we were doing here, we were just looking at P. Oops. So what we want was that Pij was simply the projection on some Xij, where Xij's were vectors in Cn. norm one. So we want actually that these projections are rank one projections on some vectors on some complex. And you see these conditions now, these conditions here that the sum of these rank one projections have to be identity. These now are equivalent to the fact that these elements xij, so it is when I goes from 1 to n, form an orthonormal basis of Cn. So what we are actually want in this quantum permutation matrices of this special type, where entries are rank one projections, is that every row and every column is actually an orthonormal basis of the Hilbert space of C to the n. So this is the algorithm we suggested to construct such matrices. So the idea is that first you start with, so remember xij lives in Cn. So basically I have a 3 tensor because I have coordinate I, coordinate j, and xij is a vector, so I have another coordinate, so I have a 3 tensor. So I just initialize it to a random tensor, so a Gaussian, maybe it's the easiest way to do this. And we have this Sinkhorn type algorithm where basically what we are doing, we are normalizing the rows. This you can always, if I give you a bunch of vectors which span the whole space, I can orthonormalize them. This is done in this normalized rows. And then I do the same for the columns. And then I compute an error and I check whether the rows and the columns are actually orthonormal bases. So since I normalize the columns last, I just have to check with the rows. So I check if now the rows are for my orthonormal basis. And I iterate this. So normalizing the rows, the columns, the rows, the columns, until the error becomes less than a threshold, or I reach a predetermined number of iterations. So this is like a very naive approach inspired by Sinkhorn, and it turns out that it works very well in practice. But we have no proof of convergence. So why we are interested in this problem? Because once we generate these quantum permutation matrices, actually, if you look at this condition that we had previously for quantum isomorphism, if you take G equals H, so if you take the same graph, what we are looking at actually are symmetries of the graph, right? So then in the classical case, P will encode a symmetry of the graph. So if you relax now P to be a quantum permutation matrix, you will find something which is like a quantum symmetry of the graph. And there is a theorem which says that if the entries, if these Pij's of the P commute, then actually this is a classical permutation matrix. So the question was, can we find symmetries of a graph G, so automorphisms, which are not classical? So can we find P's which intertwine the adjacency matrix of the graph, such that the entries don't commute? And these are called graphs which have quantum symmetries. There are some known cases, but very, very, very little is known about these graphs. So we wanted to investigate to get some numerical evidence towards existence or non-existence of these graphs, and we were able to do so with this algorithm. So basically, if you on top of these conditions, if you impose this intertwining condition, then you can find some examples of graphs which have quantum symmetry. And my time is up, so thank you very much for your attention.
Yes.